93. You guys were having Android class, isn't it?
Yes, sir.
Okay. We can wait for a few minutes, 2-3 minutes, isn't it?
Yes, sir.
Okay.
I can see that still a lot of students are missing. Only 17 of you are present. Still around 10 or 11 students are absent. Let's wait a few more minutes and you can inform your friends to join. And in the time being, it is to inform you that it is better if you can sit with a calculator, a pen and paper. I mean, it will be better for you. Pen and paper, I mean, you can just have any khata, whatever you have, and just try to sit with a calculator.
Yes, sir. Yes, sir. Total 8 classes, right, sir?
Okay, initially we have thought about that, but if needed, it can be more. It can be 9 or 10. You got my point?
Yes, sir.
So let's start. So if you remember, we were supposed to start with question answer session from the last class, and also that will also account for the revision of the last class. So I think I'll start from there.
Yes, sir.
Is it visible?
Yes, sir.
Okay, so all these things are, you already know. This is already expected time outline. Let's see how much we can go with the flow. All right, I believe all of you are familiar with this diagram. The last thing we covered was BIU. Almost everything of BIU we covered. So today we'll be starting execution unit. But before that, let's have a recap of what we learned in BIU. Okay, so let me start asking questions. So let's start with ID 103, Akash. Are you there? ID 103, Akash. Robiul Nayo, class?
103.
3.
No, take this.
Okay, Akash. Okay, fine. Okay, 115, Oyon.
9.
Yes,
Acha, 115.
Yes, sir.
115.
Yes,
Okay.
yes. Sorry.
Okay, Oyon. So do you remember in the last class we had 3 buses, right? Address bus, control bus, and data bus.
Yes, sir.
And the buses were not, I mean, there was something related with the direction of the buses. So can you tell me which bus is in which direction and why? I mean, what were the direction of the buses and why?
Sir, the data bus was bidirectional
Okay.
because the data has to be communicated in both the direction.
All right.
The control bus was from the CPU to the other buses, other units, because the CPU has to give controlling signal to other components.
Okay.
And the
What is the other bus?
address bus, sir. The address bus was from CPU to the other buses.
Yeah, why?
Because the CPU has to give the send the address of the memory or the port number to the others.
Okay. I got your answer. Okay, I'll take your answer. Okay.
Okay, sir.
All right. So let's ask, is the PowerPoint still visible?
Yes, sir.
I think it is visible. Okay. So let's ask next question to 89. Nasser, are you there?
Yes, sir.
All right, Nasser. So we already know that in 8086 you have a 20-bit address bar, right?
Yes, sir.
So for 20-bit address bus, how many hex numbers do we need to represent the address? Can you tell me? How many hex numbers or how many hex digits do we need?
So 2 to the power 20, sir.
2 to the power 20, that is your binary. I'm asking about hex. All right. So let's ask the same question to someone else. 93. Abir, are you there?
Yes, sir.
Same question. For 20-bit address bus, how many hex digits do we need to represent?
Sir, at max 5.
5. Why 5?
Sir, because the limit is to 000 and to FFFF.
Okay, now I'm asking why 5? Why not say 4 hex numbers or 4 hex digits or 6 hex digits? Why it has to be 5? What is the explanation behind it?
So that I don't know.
Oh, if you know the answer, it is again very simple. Okay. Let's 34. Muntasir.
He's not present.
He is not present. All right. 98. Zerin.
Yes, sir.
Okay. So same question. Why do we need 5 hex numbers? He already said we need 5. Why 5?
Sir, I don't know.
You also don't know. Okay.
Sir, I can answer.
What's your ID?
Sir, 88.
88. I love you. Okay, go on. Let's see.
Sir, in binary, the 4 digits, let's say 1111, they can be grouped with one hex digit. So if there are 4 ones, it
I
means.
got your answer. Okay, the answer was very simple. For each hex digit, each hex digit, we need 4 binary bits, right? So there will be 20 bits in binary. So definitely 20 divided by 4, because we need 4 bits of binary for 1 hex. So 20 divided by 4, there will be 5 hex numbers. Very simple, right?
Yes, sir.
All right. Let's ask another easy question to 141. Samadul, are you there? 141. Absent?
So he is absent.
Kotgulo absent. Okay, 16. Akib. 16. Akib. Are you there? Or is he also absent? Rubil, Akib absent naki? Koyjon absent?
Sir, he is also absent. ID 16.
Koyta absent gelo. So, okay, tell me the ones who are absent. ID 16 is absent. So far, I have called 16. He is absent. Then I called Nasir was there. Alavi was there. 91. Kais is present or absent?
So he is present.
Okay, who else were absent? Whom I called? Just tell me the IDs.
So 16, 34, 141.
16, 30, 16, 34, 141.
99.
99.
Sir, and 149, I guess, sir.
Yeah, 149. He called me. Okay. All right. So these are the people absent. Okay. So let's ask. Okay, 48. Asif.
Yes, sir.
Okay, I'll ask you the simplest question. Okay. Tell me the sequence of buses that come into operation in the read and write operation. I mean, when you read and when you write, these are two separate operations. Tell me in which sequence the buses take part in this operation.
Sir, in read and write, sir.
Yeah, in read and write only.
Sir.
Can you answer?
Sir, please give me a moment, sir, please. Sir, maybe, sir, I don't get it correctly, sir.
So you can't. Okay.
Sir, I can answer, sir.
What ID?
Sir, 16 batch 35.
16 by 35. Okay, go on. Say.
Sir, in the read operation, sir, the buses that operate simultaneously are the address bus, control bus, and the data bus.
They operate. I'm not asking the simultaneous operation. I'm asking the order of operation. First of all, which bus?
Okay, sir.
Okay,
in the read operation, sir, first of all, the address bus will, sir, go on.
Okay,
and then the control bus, and then the data bus. In the write operation, sir, the first the address bus will go on, then the data bus, then the control bus.
Yeah. Okay. So I'll take your answer. Okay, let's ask someone else. Robiul, অবস্থা দেখছিস? হ্যাঁ?
Sir, I talked with Robil sir yesterday about the thing with my friend 16 batch 147. Sir, he is not able to join the class. I told sir Robil sir yesterday.
Yes,
Okay.
yes.
রবিউল দেখছিস?
হ্যাঁ।
সিম্পল কোশ্চেন, এখনো কিন্তু ওই কোশ্চেন করিই নাই এখনো। Okay, let's ask someone else a few other questions. Okay, this question is open. Okay, this question is open, anyone can answer. So Rubil also discussed this part very clearly. So you can see that we have got two, what I can say, arithmetic units or logical circuits, one at the BIU and the other at the execution unit. So why do we need two circuits instead of one? We could have simply used one LO. Okay, tell me the ID, who wants to answer?
Sir, 92.
92. Okay, 92, continue. Bolo.
Sir, for a simultaneous operation of a fetch and execution, for execution we need arithmetic logic unit, and by same time we are fetching the data from memory, so we need summation from BI unit, arithmetic operation from BI unit, and at the same time arithmetic logic unit can execute that other commands.
All right, so for the simultaneous operation we do need two circuits, right? Otherwise we
Yes,
would
sir.
have been stuck with one operation. Is it clear, everyone? These
Yes,
are
sir.
the very few basic questions. Yeah.
Yes, sir.
Okay, what? Say.
No, sir, it is clear.
It is clear. Okay, these were the very few basic things we wanted to clear up, but actually I'm not so happy with your class performance. I expected a bit more from this section. There were some basic questions which you could not answer, so that's depressing. Okay, let's move on. So these were regarding your class performance, so let's move on. So this one I think is clear. Moving on to the prefetch queue, I think there was a question, why 6 bytes, and I think the answer is very simple. The maximum instruction that we can have in 8086 contains 6 bytes, right?
Yes, sir.
The largest instruction. Very simple. All right, so these were all discussed in the previous class, prefetch queue.
Sir, I have a question, sir.
Okay, go.
Sir, I didn't understand the part, sir. In the address bus, there are 20 bits. And in the 8086 memory, it is actually of 16 bits. So in order to compensate that, we are converting 20 bits to 16 bits in different segments. So there are actually 2 to the power 4 segments, right, sir?
Yeah, segments 2 to the power 4, yeah.
And sir, from that, we are actually taking 4 segments, or sir, where are the other segments actually? I didn't understand that part.
Okay, you have 4 segments. You can access whichever segments you like. It depends on which segment you will be accessing when. For this particular time, we are generally accessing our instructions, the codes, which is normally in the code segment. So you are currently accessing the code segment. As we move on, you will understand when we will be accessing stack segment, when we will be accessing data segment. All these things you will learn gradually when we'll go for coding. Is it okay?
But actually there are 16 segments in total, sir.
It's not that there are 16 segments, there can be 16 segments.
Oh, okay.
There can be 16 segments. How many segments will be there totally depends on the microprocessor, but there can be 16 segments
at maximum, sir.
At max. No, not max, mean.
Oh, sorry.
Why I'm saying minimum, you will understand in today's class. So I'm saying, sir, that there can be a minimum of 16 segments. Why did I say minimum, not maximum? You will understand in today's class.
Okay.
Okay, one important question actually I forgot to ask. Yeah, I think I should ask that. Okay, so all right, let me just try to highlight. All right, so these are, what are these called? ES is extra segment, then code segment, stack segment, and data segment. Am I right? Are these called extra segment, code segment, stack segment, and data segment?
Yes, sir. Yes, sir.
Everyone, are you sure that these are called extra segment, code segment, stack segment, and data segment?
Yes, sir.
Okay, so is the size of stack segment from 0000H to FFFFH? Is it so?
No, sir.
No, sir.
So
No, sir.
all of you just okay, wait. All of you just said that this is extra segment. So if it is extra segment, it is supposed to start from 0000 and end up to FFFH, right?
Yes, sir.
Then
Sir,
okay. All right. So these are
the address
actually
is the same.
these.
Address size.
Wait. So these are known as your registers. Okay.
Yes, sir.
Remember, so this one is actually your ES register, this is your CS register, this is SS register, and this is your DS register. The basic difference is your ES is actually in your memory where it has a size of this range. That is okay. But in this particular place, I mean in BIU, ES contains, ES register contains the starting address of ES. Is it clear? ES contains the starting
Yes, sir.
register of ES. CS contains the starting address of CS. SS contains the starting address of SS. And DS contains the starting address of DS. So whenever you try to access any of this segment, over here you can see it is written ACG. So this ACG will be taken from these values. So if you want to access data segment, then the value of this SEG will come from this DS register. Clear? Which will be the starting address.
Yes,
Clear?
sir.
Okay. Let's go on. Okay, this was Y6 bits. We already know. Okay, all these things we already know that it will take 2 bytes of data at a time because this is a 16-bit data line, 16-bit bus. So it will take 2 bytes at a time. You already know all these things. So this one will come, then this one will come again. Okay, we already know all these things. Move on. Okay, there was a task. What is the drawback of pipelining? Can anyone answer? Open
Yes,
floor.
sir.
Yes, sir.
Yes, sir.
I think all of you are supposed to be able to answer because this was
Yes.
given in your home task, right?
Sir.
Yes, sir.
Okay, so let me explain. No need to answer because you already did that. So the problem was, okay, so this one is what this is saying. So first of all, say this one is being executed. Okay, first of all, this command is being executed here, then this command is coming over here, so it is going on like this. But say at some instance we have got this command which tells us to jump to 106H. I mean, when this command is decoded, okay, assume that when this command is being decoded, it tells the microprocessor that you need to jump to 106H, that is you need to jump over here. But what do you have in this prefetch queue? You have these corresponding commands, isn't it? Because this is
Yes,
how
sir.
your prefetch queue is arranged. So in such cases, what will happen is whatever you had in the prefetch queue will be flashed or erased or whatever you say. Okay, it will be completely cleared from the prefetch queue. Then it will again start loading the prefetch queue from 106H. So this is the drawback of pipelining, because if we ever encounter any operation where we need to jump, then the prefetch queue will be deleted. Now try to understand what is actually happening. So all of you already know that your microprocessor works on clock pulses, right?
Yes, sir.
Sorry. Okay, so all of you already know that your microprocessor works on clock pulses. So, okay, clock pulses. So what will happen is, in one pulse, I mean, in the particular pulse, when your execution unit will decode this portion, it will tell to jump to 106H. But instantly, you cannot load this 106H over here, right? Because this 106H will have to come over there. Then the next one will come over there, and your 106 will go over there. Again, it will come. Again, it will come. Right? It will come gradually.
Yes, sir.
So you will need a lot of clock pulses for this 106H to reach over here. So in the meantime, your execution unit will be sitting idle. It will not do anything during those clock pulses. So that is the main drawback we have. Clear,
Yes, sir.
everyone?
Sir, in my assignment, I looked from the internet, and it said that they need to be synced, the clock pulses. Is it correct answer?
Of course, synced for what? Tell me first that. What did you mean by synced?
Sir, sync between the execution and collecting in the fetch.
Yeah, the meaning is that, see, your clock pulses are something like this, right? So in each of these pulses, your processor operates. So say you are at this clock pulse. So in this particular clock pulse, your execution unit is executing something. At the same time, your BIU is fetching something. Is it clear? This is what is synced.
Yes, sir.
All right. But when we are in this type of situation, then we will miss a few pulses where your execution unit will not do anything. Say again, we are continuing from this clock pulse. So again, at this particular clock pulse, your execution unit will start executing something. At the same time, your BIU will keep on fetching the corresponding data or corresponding instruction. All right. Clear?
Yes, sir. That's correct.
Okay. So let's move on. So, okay. So these were all regarding your BIU drawback pipelining. I mean, everything so far, whatever we discussed was something that we already discussed in the previous lab. So now we'll be moving on to the execution unit. Okay. So you can see this part, execution unit. Do you see one part, control unit?
Yes, sir.
So if you remember, over here is your prefetch queue, right?
Yes, sir.
Over here is your prefetch queue. So every instruction from the prefetch queue, first of all, comes to the control system. This is basically the decoder of the microprocessor. So all the commands you get in binary. So this control system decodes that binary and tries to make a sense of what that instruction means. Once your control system decodes your instruction, then this control system will send necessary information to whomever is needed based on the decoded instruction. Am I clear?
Yes, sir.
Okay, so every instruction first of all will come to the control unit or control system where it will be decoded. After being decoded, the control system will decide what we need to do. There are a few things over here in the execution unit. As you can see, we have got 1, 2, 3, 4, 5, 6, 7, 8. We have got 8 registers. Among these 8 registers, you have got 4 general purpose registers, and we have got another 4 which are index and point registers. So we will get to know all these things in the time being. Over here, we have got 2 separate registers. One is operands and another is flags. So we will get to know all these things.
Yes, sir.
Okay, so first of all, let's get what we mean by general purpose registers. These registers are open for use for the programmer or for us, for anyone who codes. Okay, these are open for us. As you can see, each register AH and AL, they all are 16 bits. Okay, this 16 bits is divided into 2 portions, AL and AH. So very obvious, AL is 8 bits and AH is 8 bits. So as a programmer, you have the liberty to address either the entire AX register, or you can separately address AH and AL register. So whenever you write a code where you will write AX, that means you will be accessing 16 bits at the same time. Whenever you will write AL, that means you will be accessing the lower 8 bits of this AX register. If you write AH, you will be accessing the higher 8 bits of this register, or the lower byte and the higher byte. Is it clear up to this?
Yes, sir.
Okay, so these are your temporary memory. As I already said, the programmer has access to these segments or registers. Okay, so what
Can the class be recorded?
Robiul,
Yes.
I think the class will be recorded. I mean, the next class will be recorded, not this class.
Okay, sir.
Okay, so
and we'll upload by today, inshallah. We'll upload by today.
you'll get the recorded version. Don't worry. Okay, so as I was discussing, AX is 16 bytes. You can see. So these are your lower bits, and this is your higher bits. Very simple. So same thing for BX register as well. You have got lower and higher. Same thing for CX and DX. All right. Is it clear up to this?
Yes, sir.
All right. Moving on. So this is a normal description of what are the function of these registers. We will not get into very details or in deep of these functions, because you will learn all these things as we move on, or as we go on coding, you will learn the various uses of this register. For the time being, you need to keep in mind a few things. Like you can see that in case of multiplication and division, one of the numbers involved must be either in AX or AL. This is the only thing you need to remember for the time being. So when, maybe from the next class you will start coding. So whenever you are coding, if you ever want to multiply or divide, one of the numbers must be either in AX or AL. Clear?
Yes, sir.
Similarly, BX has got some instruction requirement. Then similarly, we have got for CX as well. Another thing for the timing you need to know is DX. So DX is also used in multiplication and division, and it is used in input output operations. That means in any situation, if you want to see your result, or if you want to display your result must be stored in DX. All right, because this is the only register which is used in input output operations. So these are the only things for the timing you need to keep in mind. The same
Sir,
thing goes.
in
Okay,
AA, what is the problem for multiplication and division? Like, what does it mean that it should be in AL and AX?
So these are the laws actually. Okay, so whoever designed this microprocessor, whenever they made these rules. So actually I still don't know the explanation why it has to be in AX or AL, but this is the rule that we always follow. This is the rule that DX will be used in input output operation, not any other register. So these are the rules, and we never question those rules actually. All right.
Okay.
Sir, can you repeat the rules again?
Like it's written already over here. For the time being, we are only interested in two things. For division or multiplication, one of the numbers involved must be either in AX or AL. Simple. And if you want to see any output, or if you want to display any output, that particular output should be stored in DX, because it is used in input output operations. You can see that the other registers are not used in input output operation. Only DX is used in input output operations. Clear?
Yes, sir.
Actually, these rules are made, so far what I understand or what I believe, is to simplify the operation. Maybe it becomes, we all need to fabricate these things. Whatever we are learning are like theoretical things, but these needs to be fabricated and sold to customers, right? So I think these particular rules simplify the fabrication or simplify the operation procedures. All right.
Yes, sir.
For the timing, or if you're interested, you can look it up in the Google or somewhere else. I don't know, maybe there are explanations.
Yes, sir. So it means that if we initialize variable A, we will say initialize AL, then the variable, and then the next variable will be initialize BL or BH and the next variable, right?
We do not actually initialize. I don't know what you are meaning by initialize. These registers are already there. You can store temporary values in these particular registers. All right. So if that is what you meant by initialize, yeah, you are right. You can. That is how you save the numbers on those registers.
Yes, sir. Yes, sir.
Okay, the use of the registers of AX, BX, CX, all those things we'll be learning in the next class. But how to use those things and why you are using. So anyway, we'll go for coding. Maybe we'll show just one thing today. You'll learn things, inshallah, in next class.
Okay, sir.
So the same thing for this stack pointer, base pointer, source index, and destination index. We will not be discussing in details for the time being, because as I said, as we move on in the later classes, when you start coding, you will learn by using what is the function. When you are using stack pointer, when you are using base pointer, all these things you will learn. But these are just some of the functions. These are theoretical knowledge. You can just have a read. You can just go through what is this used for accessing stack segment. Okay, so you will gradually learn all these things. For the time being, let it just be over here. Clear?
Yes, sir.
All right, so let's see what happens over here. Okay, as you can see, this is the code that you run right in your assembly language, move AL05H. So this one is basically your 05H, and this one is basically the opcode for move AL. So whenever this instruction will come to this control system, I think it is already, yeah, okay, yeah. So whenever this instruction will come over here, you can see that it has already been decoded. So if it is decoded over here, by decoding it will realize that this is my command, move AL. So that means your control system will understand that I need to move some value to AL, which value will automatically come from the next instruction, because this instruction, this particular instruction gives the command that move AL. Then we already know that this is your destination, right? So there has to be a source, and we know that by default, first of all, we give the destination, then we give the source. So definitely the source will be the next instruction. This is what the control system will understand. So it will fetch the next instruction. So once fetching, it will understand that this is supposed to move to AL. So as you can see, this instruction moves to AL. Clear up to this?
Yes, sir.
Okay. So comes the next instruction, the same thing. Again, it decodes and it sees that the instruction is move BL. So again, it will wait for the corresponding instruction, because there is something in the next instruction that will actually be moved to BL. And you can see that this value will move to BL. Now, over here, these are just examples, okay? Instead of BL and AL, you can use AH and BH as well. That is totally up to you. Completely up to the programmer. Clear?
Yes, sir.
Okay. Now this is the last command, that is add AL and BL. Once the control system decodes this command, that whenever this instruction will come over here in the control system, your control system will decode it, and it will understand that I need to add whatever is there in AL and BL. So your control system will instruct this AL and BL that send me the values to the ALU. See, by default, your AX or BX or AL or BL will not send the data. All right. Someone needs to tell this AL and BL that I need your data, or you send the data to that place. For the time being, AL and BL will keep the data within itself. Whenever someone will ask, that is when they will send the data. So first of all, the value of AL and BL will go. Now they will, they will be in the arithmetic logic unit. The control system will tell the ALU that I have sent two values to you. You add those two values. So your arithmetic logic unit will add those two values. Now where will it keep it? Your control system knows that this command means that whatever result I get will be stored in AL or BL. Tell me, whatever result we get from this ALU, it will be stored in AL or BL?
Or DH or...
It won't be stored.
It won't be stored anywhere.
So it should be stored somewhere, but...
So I think, I don't know, sir.
Okay, you don't know. You already did MATLAB, right?
Yes,
You coded in MATLAB.
Yes, sir.
Yes, sir.
Okay, so whenever you write C is equal to C plus 1, what happens? Tell me.
So the value of C increases and it stores in that C again.
Okay, so isn't this command exactly equal to add CL comma 1 in assembly? Or sorry, not CL, it will be C. Sorry. So add C comma 1. Isn't it the same instruction in assembly?
Yes, sir.
Yes, sir.
So where should it store?
Sir.
The AL.
AL, sir.
Exactly. It will store in AL. All right. So after this addition, the control system will tell the ALU that send the address and store in AL. So as you can see, the value will go to the bus and it will be stored in
AL.
AL. Is it clear?
Yes, sir.
Yes, sir.
Okay. Why not BL? Okay. So let me answer
So
your
if
question.
you just
Okay.
revert, then it will be, I think.
Okay, yeah. Why not? Okay, okay.
stored in
So
BL.
when you wrote in MATLAB, C is equal to say C plus N, where C was initialized to 2, N was initialized to 4. What was the value of C after this line is executed? What is the value of C? 6. And what is the value of N? So now if I ask you, why is the value of C6 and not the value of N6? If you had written N is equal to C plus N, then the value of N would have been 6 and the value of C would have been 2, right? So the same thing is over here. We are writing add AL comma BL. That's why the answer is being stored in AL. If we had written, say, add BL comma AL, then the answer would have been stored in
BL.
BL. Is it clear now?
Yes, sir.
Clear? Okay. Moving on. All right. Now we will learn what is the function of these operands. You can see this is also a 16-bit general purpose register. So we will try to understand what is the operation. I mean, what is the function of these operands? Clear?
Yes, sir.
Okay. Now, okay, let me pen. Okay. What will happen when we execute this command? Move AX, 1, 2, 3, 4 H. What will happen?
So it will move 1, 2, 3, 4 H to AX.
AX. So see, your AX will contain this value. Clear everyone up to this? When we write this command, move BX 5, 6, 7, 8, 8, what will happen? Your BX will get this value.
Yes, sir.
When we write exchange, this is the assembly language code for exchange. Okay, this is the
Yes, sir.
command
It will.
for exchange.
It will
So
flip
what
the
happens?
value.
We want to exchange the values. So tell me, how will this exchange operation takes place? So the value of AX will come to BX, and then the value of BX will go to AX. Is it correct?
Yes, sir.
Exactly. It needs to store in a temporary variable, because if AX directly sends its values to BX, then the contents of AX will be placed in BX and BX will lose its original content. So again, when BX will try to send AX, then BX will be sending the same value that AX already have, isn't it? Did you get my
Yes,
point?
sir. Yes, sir. Yes, sir.
So definitely we need someone in between who will temporarily hold the data, and that is what your operand does. So see, first of all, the value of BX will come to the operand, then the value of AX will move to the place of BX, and then the value which was stored in operands will move to AX. So for this type of commands, your operand registers are used. Now remember that these registers are not accessible by the programmer. A programmer cannot access the operands register. These are kept by the microprocessor for its own use. There are 1,000 of uses of these operands. Okay, this is just one of the examples. So
Yes,
for
sir.
this special type of operations, the microprocessor uses the operands register. Clear? A programmer cannot access the operands register. A programmer can only access AX, BX, CX, and DX. Clear up to this?
Yes, sir.
Okay. Moving on. There was another thing called the flags. All right. So the flag is also a 16-bit register. As you can see, this one is for your carry flag, parity flag, auxiliary flag. I mean, a lot of flags are there. All of this you will learn when we'll discuss flag in lab 4. For the time being, just know the names and just know that these flags are called status flags and these flags are called control flags. Now there is a reason why there are two names. So why there are two names is, whenever we code, we execute commands, right?
Yes, sir.
Yes, sir.
We give commands, like if I say add AL comma BL, this is one of the commands. If we write move AL comma 02H, this is what? Another command, right?
Yes,
So
sir.
these are the commands that we execute. These status flags updates its position every time you execute a single command. Like when you execute this particular line in the code, all these flags will update its position. I mean, how they will update, you will learn, as I said, in lab 4. Okay, when you will learn, just know for the time being is based on their behavior, they will update their position after one line is executed. When you execute this line, again all of them will update their position. So after executing each and every command, all of these flags will be updating their positions. Clear?
Yes, sir.
But these control flags are kept for the microprocessor for managing the control operation of the microprocessor. These will not be updated after execution of every command you do or every command you make. Clear?
Yes,
Is
sir.
it okay? Okay, for today's lab, for the time being, I think we will just take a look at the sign flag. Just a very simple example we will take. So see over here, we have got a command move AL 58. So you already know AL will take the value 58, BL will take the value 28. Now this one is your assembly code language for compare. So if you write compare AL comma BL, what will happen? Tell me. What actually happens? Exactly, it will give the difference, right? So what are the things that can happen? Your AL can be greater than BL. I mean, for this particular example, AL is greater than BL, but based on these values, these are the possible scenarios that can take place, isn't it?
Yes, sir.
Your AL can be greater than BL, or your AL can be smaller than BL, or your AL can be equal to BL. There cannot be any other possible scenario. So for this particular cases, what will happen? If your AL is greater than BL, then AL minus BL will give you a positive number, right?
Yes, sir.
If AL is smaller than BL, AL minus BL will give us a negative number. If AL and BL are equal, then it will give you a 0. So every time we are finding the difference because we have used compare AL comma BL. If we had written compare BL comma AL, then all this thing would have been exact reverse, isn't it?
Yes, sir.
Okay, so you do understand that portion, right?
Yes, sir.
Yes, sir.
Compare AL BL means AL minus BL. Compare BL AL means BL minus AL. Okay. Okay. So see now what happens if the result is positive, the sign flag will be 0. If the result is negative, the sign flag will be 1. If the result is 0, then 0 flag will be 1. Okay, this is another flag. 0 flag will be 1 and the result is 0. So let me ask you a question. If this is 0, what will be the value of sign flag for this particular case when AL is equal to BL? What will be sign flag? 0 or 1?
0. Yeah. I think it's 0.
It will be 0 because 0 is considered as a positive number, isn't it?
Yes, sir.
Okay. So these were the things. Okay, why it is becoming 0 and 1, you will understand gradually. In today's class, you will understand. Just know that if the result is positive, sign flag will be 0. If the result is negative, sign flag will be 1. As simple as it is. Okay. And if the result is 0, 0 flag will be 1. All right.
Yes, sir. Very easy, sir.
Yeah, simple. Okay, so this was again, I mean, the execution unit, what happens when you go for compare AL, BL. So see, it is already written, it will do the subtraction portion. Okay. So first of all, the contents of AL and BL will come, then they will subtract whatever value they get. Based on that, the sign flag will be updated. Now you can see there are two terms, MSB. Can anyone tell me what is MSB?
The most significant bit.
Exactly, most significant bit. So okay, so for this particular byte, what is the value of your MSB?
0.
Is it 0 or is it is 1?
Sir, there will be one overflow.
There will be one overflow. Well, we have not yet entered any such complex scenarios. Okay, we are still in the simple scenarios. Okay, why it should be 0? Tell me. The most significant bit will be bit 7. Anyone else with any other opinion?
binary numbers we use like from right
sorry,
to
say
left.
again.
So in binary numbers we use this chronology from right to left.
Yeah, all right. So his explanation was correct. Okay, so this one is your MSB, and this one, what is the name of this one?
LSB, sir.
LSB, sir, least significant.
Exactly. So this is MSB and this is LSB. So your sign flag depends on your MSB. Okay. So if the MSB is 1, your sign flag is 1. If the MSB is 0, your sign flag is 0. Now, the question is definitely, if the MSB is 1, the sign flag 1 means the number is negative. Why is that? Isn't it?
Yes, sir.
So
Yes,
we will discuss it. This will be the next thing we'll be discussing in today's class. Okay. But for the timing, just know that if MSB is 1, sign flag is 1. If MSB is 0, sign flag is 0. Easy, simple, clear?
Yes, sir.
Okay, someone was talking about carry. See, carry will come, I mean, carry will not come over here. Okay, carry will come whenever you exceed the size limit. So this is simply 8 bytes, right? Sorry, 8 bits. So you are still not exceeding the size, because over here you have got 8 bits, and all these buses, they can carry, you know, that 16 bits, isn't it? So still there will be no carry. You will encounter carry whenever you will exceed the size. If you ever have a 17-bit answer, then that is when your MSB will become the carry. All right, you will learn all these things gradually as we move on. All right. Okay, let's go to memory segmentation non-overlap. So this is what I was discussing. I think in the beginning of the class I said that we can have a minimum of 16 segments, not maximum. So this is what we'll be discussing now. Okay, why did I say minimum and not maximum and something like that? So we discussed that your memory segments in this way in the last class, that extra segment, stack segment, code segment, data segment, and you can see that none of the segments are overlapping, right? And we also discussed why each segment is 64 kilobyte, why there are 16 segments. All these things are already discussed. So this is the code segment. You already know the size is from 000 up to FFFH. So you already know this is how these are arranged. You already know how to find the physical address. Already we discussed why we multiply by 10h. All these things are clear, I believe.
Yes, sir.
If you still have question, you can ask. Okay, there is no problem with asking questions. You can ask any question, even if you think the question is silly. No problem with that. You can ask. All right.
Yes, sir.
Okay, let's move on. So this is what I wanted to explain. Memory segments overlapping. In real scenario, actually your memory segments are overlapping. They are not non-overlapping. Okay, there are overlap in memories. That means you can see that this is your code segment, this violet line. Okay, let me highlight. Okay, see, it is already written. So this is your code segment, this portion is your code segment, and your this portion is your stack segment. Yes, stack segment. You can see that this portion is overlapped. Can you see?
Yes, sir.
This portion is overlapped.
Yes, sir.
Actually your segments are overlapped based on the microprocessor. I mean, there is a provision in which the microprocessor allows the various segments to be overlapped. Okay, so if we move on, see, you can see that, I mean, these are overlapping segments. Of course you will have the question then, for one segment, for one particular physical address, which segment will hold the answer, which segment will hold the address? I know you have these questions. Just bear with me for the time being, then I'll let you ask questions. So this is what happens. You have memory segmentation overlapping.
Yes,
okay,
sir.
Before that, all right. So now it gives you the answer why I said we can have minimum 16 segments. So see, for making 16 segments, each segment has to be 64 of kilobyte, right? That has to be the size. Now, if there are overlapping, say you have got one segment, say data segment, instead of 64 kilobyte, the size becomes, say, how much? Say
50, sir.
Say 32 kilobytes, say, just for example.
Yes, sir.
Say we got another segment, let's take a stack segment. Say the size becomes 20 kilobyte.
Yes, sir.
So what is happening? as you move on, you will see that you have finished all the 16 segments in less than 1 megabyte of memory, which is allocated for the microprocessor, right?
Yes, sir.
Yes, sir.
So you still have few memory segments, few memory slots left where you can assign more segments. Is it clear?
Yes, sir.
That's why I said I can have a minimum of 16 segments, but a maximum how many segments I have is not determined because it totally depends on the microprocessor. Is it clear, everyone?
Yes, sir.
Yes, sir.
Okay, any question up to this? Any question?
Sir, can you please repeat this
Sir,
part again?
sir, can I have a question, sir.
Say.
Sir, due to overlapping, sir, if we have the smaller segments, sir, how does the overlapping working, sir? Because the maximum limit is 1 MB. So if we have these smaller segments, we will get a much lower amount of 60 or combined 16 segment data. So why it is, sir, helping for?
I mean, how it is helping, right?
Yes, sir. Yes, sir.
Okay, so let me come gradually. So first of all, I mean, when can a segment be less than 64 kilobyte? Let's discuss that portion first. Okay, when can it be less than 64 kilobytes? Say you have got code segment. The allocated size for code segment is from, I mean, like 2 to the power how much? Tell me.
16.
Exactly, 2 to the power 16 bits. Say the contents that you have in code segment is completed in 2 to the power 12 bits, say for particular example. Okay, so you still have 2 to the power 4 bits left, which is already allocated for the control segment, isn't it? But you do not need these bytes, because whatever I have in the control segment, sorry, code segment, whatever I have, the contents in code segment is already covered in 2 to the power 12 bits. So should I keep these 2 to the power 4 bits empty?
No, sir.
No, sir.
No, sir.
Because this is an inadequate use or improper use of your memory segment. So whichever segment is following the code segment, say stack segment. So the following segment after control segment is stack segment. So what happens is stack segment, I mean, these bits go to the stack segment. But remember, these were already allocated for the code segment,
Yes,
but
sir.
you are allocating this for the stack segment. So that means these 2 to the power 4 bits can be accessed by either code segment or stack segment, because what did we say? Your instruction pointer or the pointer size can be from 0000 up to FFFF, isn't it?
Yes, sir.
So definitely for a particular size of that pointer, you can come in this location, right? For the code segment, are you getting me?
Yes, sir.
Sir.
বুঝতেছো এই পর্যন্ত?
Yes, sir.
Okay, so the same thing is true also for stack segment, because you are allowing stack segment to have these bits. So definitely for the stack segment pointer, there will be some particular value that can access this value, right?
Yes, sir.
So what I'm trying to say is these 2 to the power 4 bits is accessible by both this code segment and this stack segment. That's why we say that this is overlapping. Is it clear?
Yes, sir.
Up to this? Yeah, any question?
Sir, instead of using in CS 2 to the power 12 bits, let's say, sir, we need some execution that needs 2 to the power 17 bits. Let's say, sir. So will it go to the stack segment and take some bits from there?
No, you cannot have 2 to the power 17 bits for a particular segment, because whenever you exceed 2 to the power 16 bit, you need 5 bits in hex, right?
Yes,
if you remember, and
yes,
your
sir.
address bus is 16 bit, your address bus cannot be 17 bit. So there cannot be 2 to the power 17 bits for a particular segment. Right? That was the initial problem. Why are we doing segmentation? To solve that particular problem, isn't it?
Yes, yes.
Okay, so that cannot be that. So that's why I said that there can be a minimum of 16 segments. if any segment goes beyond this size, you cannot have 16 segments, right?
Yes, sir.
Okay. Now there was a question
Okay,
that
Arif, just I want to add something here. That in case of like say data, there is an extra segment. Can you see? There is an extra segment.
Yes,
So what I understand from his question is that let us say for data segment you have more data than this limit. So the microprocessor actually will decide in which segment the extra data will be stored. Maybe in extra segment, or it can create other segments. Have you got my point? The person
Did you
who
get
has
your
asked
answer?
last.
sir, can you repeat?
What I'm saying, let us say in data segment you can have many data, like you have an array, you have so many variables. So maybe it happened that okay, data segment like the contents of data segment exceeding the limit of 64 kilobyte. So it may happen that the extra data can be saved in extra segment, or that will be decided by your microprocessor.
So his question was basically what happens if we ever have 2 to the power, if we need 2 to the power 17 bits. Like what Robil is trying to explain, or what he explained, is in data segment, say we stored the data and say the size of the data segment is 64 kilobyte. Say we already filled up this 64 kilobyte and we still need to store some more data. Okay, that was the initial question. So what will happen? So those values will be stored maybe in extra segment or some any other segment decided by the microprocessor, isn't it, Robil? ঠিক আছে না?
Yes, I was trying to say that, and you can see that in extra segment, the function of extra segment is something like that. It can store data also. Okay.
Is it okay up to this?
Yes, sir. Another question. Sir,
say.
suppose at first there is the code segment, there is 2 to the power 12 bits, and after that the stack segment starts. And what if sometimes after that the code segment's data increases from 2 to the power 12 bit to some extra 2 to the power 16 or?
Okay, let me take the question, Arif. Okay, thing is that every time you run a program, it is not fixed that what's the address where the code segment will start. So whenever you execute a program, so the microprocessor decides where the code segment will start, where the stack segment will start. So it is not fixed. It will be changing. Have you got my point?
Yes, sir.
Okay, so I think there was another question which I had to address, like why, I mean, the question was why do we need overlapping? What happens when we have extra segments, right? That was the question, isn't it?
Yes, sir.
So let us talk, I mean, let us try to answer this question from a general perspective. Say you are a publisher, okay? You are a publisher and you are trying to publish a book. So the limitation you have is currently 500 pages, okay? That is the limitation you have. And you decide that for each chapter you will allocate 50 pages, okay?
Okay, sir.
So how many chapters can you have?
10 chapters.
Okay, so you can have 10 chapters. Okay, so you can have 10 chapters. Now now you invite 10 authors, okay? You invite 10 authors to write these 10 chapters. But say you find that say almost all of the authors wrote these chapters about, say some wrote about in 6 pages, some wrote about in 7 pages and something like that. So at the end, after getting everything, you see that you still have around 20 pages left. So what will you do? Tell me.
So we can add more chapters.
Why do you need more chapters? Why are you adding more chapters?
So we have left pages.
Exactly. So see, you are answering like a microprocessor. So the microprocessor will think the same thing. So I have got extra places, so why should I leave them like this? So I can have extra segment over there. I can use them for some special uses.
The remaining spaces for another purpose.
Exactly. Is it clear now?
Yes, sir.
Clear everyone up to this?
Yes, sir.
Yes, sir. Yes, sir.
It depends on the microprocessor. It is actually not that simple, okay? The way we are discussing, actually things are not that simple, okay? It depends on the microprocessor. All right.
The flow of space allocation, sir, is not fixed?
No, the space allocations are not fixed.
Okay.
All right, moving on. So if we are clear up to this, let's try to solve this math. That's why I told you that try to sit with a pen and paper and a calculator. So the question is, for the memory location whose physical address is specified by 1256A8. So this is your physical address. Give the address in segment offset form for segments 1256H and 1240H. So try to solve it. Let me give you some time. Take 3 or 4 minutes. Try to solve it. I can write the formula over here. Exactly. So I can write the formula over here for you to help. So your formula is your physical address will be equal to your code segment into 10H plus offset, right? Where all the values are in hex. So this is the formula that you need to use. So use this formula and try to find the answer. So let me give you how many minutes? I think 2 to 3 minutes should be more than enough. So let's take 3 minutes. After that, I'll discuss the answer. In the meantime, if you can find the answer, please let me know.
Sir, I have done it.
Where is it?
Yes, sir.
Okay, let's wait for others also. Okay. You have 2 minutes. Please try to solve it. Okay, could you solve? Anyone else?
Sir, I did the first one.
Okay, at least the first one is fine. Anyone else? Khali duijon. Okay. Okay, let's see the solution. Okay, it is actually very, very, very simple. So what
Yes,
is my
sir.
physical address? My okay, let me start pen. Okay, what is my physical address? My physical address is 1256A. Okay, for simplicity, I'm not writing H because all the numbers are already in X.
Yes,
So
sir.
what is my one of the segments? Say let's continue with 1265H first. So if I multiply 1256 with 10, I will end up getting 12560, right? So let's write over here for offset, let's write X. This is one of the example. This is one of the solution. What is the another one? Again, the physical address is same. So 1256A, this will be equal to, corresponding these segments. So this will be 12400, right? If I multiply with 10, you are understanding this part, right? I'm
Yes, sir. Yes, sir.
cutting in a bit short. And say let's write over here Y. So what will be the value of X and what will be the value of Y? You simply put it in your calculator, take it in your hex mode, and if you do the subtraction, you will get the subtraction. You will get the result. What will be the value? Tell me.
Sir, A.
First one is A and the second one is 16A.
A, and what will be the value of Y?
16A.
16A, definitely. So for this 1256, what will be your answer? Your answer will be 1256. Then we will give a colon. After that, what we will write? Tell me.
A.
A.
We will
0,
write
0, 0,
000 A.
A.
And for this one, we will write 1240, then
0016A.
00, sorry, 016. Yeah. Sorry, wait. It will be 1240, then 016A. So what I'm saying, see, this address and this address, they both represent the same physical address. So let's write just over here hex and hex. Is it clear, everyone?
Yes, sir.
Any question? Any question?
Sir, could you repeat how it represents the same physical address?
How it represents the same physical address. That is what I think we discussed in this particular slide. If that particular physical address is somewhere in these bits, which is shared by both these segments, then from these both segments, you will be able to access that particular address, isn't it?
Yes, sir.
Right?
Yes, sir.
So assume the address that we currently got is somewhere over here. This is the portion which is overlapped, right?
Yes, sir.
Yes, sir.
So that means what? This physical address can be accessed by both these segments, isn't it?
Yes, sir.
So that is exactly what happened over here. This is your one segment, 1256 is one segment, 1240 is another segment. But both of these will give you the same physical address because this is being overlapped.
Yes, sir.
Clear up to this?
Yes, sir.
Any question?
No, sir.
All right, let's move on. Now we need to come to unsigned and signed interpretation. The first thing it says is, try to see, it says interpretation. So why it says interpretation, we will discuss after we finish discussing this. All right, so you already know. If we already know about MSB, this is a very simple. If LSB is 0, then the number is even. If LSB is 1, the number is odd. I think you already knew this portion, right?
Yes, sir.
Based on LSB, this is very simple. All right, as you can see, this is your unsigned number. So in unsigned, 101 will represent 5. But if you go for signed interpretation, 101 will mean -3.
Yes,
Here,
sir.
because the first one will signify a negative number, the rest will signify the number. So this one is for minus and this one is for your number. Is it clear?
Yes, sir.
Yes, sir.
Okay, for the timing, do you need a break or should I continue?
Sir, little bit break will be better.
It will be better, sir. Yes, sir.
Okay, so let's have a 5-minute break. We'll again start at 12.
Okay, sir.
Okay, by this time, should I call the student ID? So that will be easier for me to take the attendance.
Attendance niya na.
Okay, 35, 16
Yes,
batch, 35, 16 batch.
Yes, sir.
Okay, then. Uh, 09.
Yes, sir.
13,
Yes, sir.
16, 33,
Yes, sir.
then 38, 138. Sorry, why is name is here? Sorry, it should be 38, only 38.
Sir,
38.
there is no 38, sir.
There is no 38 in this section, sir. 138 is.
Oh, okay. So I have got his number. Just twice. Okay, 48.
Yes, sir.
88.
Yes, sir. Sir, could you check
89.
my attendance? Hello.
Yes, yes.
Sir, for my last class, I was doing the class from CNG, sir.
Okay, you are in the Zoom meeting, so I have got your attendance.
Okay, sir.
89.
Yes, sir.
Then 91.
Yes, sir. Sir, last
90.
class my headphone was not working, sir.
Okay,
Sir, please
you are
consider.
present in the last class.
Yes, sir.
92.
Yes, sir.
Then 93. 93. 98.
Yes, sir.
93 is present, isn't it? 93 is the CR.
Yes, sir.
He was here, I think.
Yes, sir.
98.
Yes, sir.
99.
Yes, sir.
103.
Yes, sir.
109.
Yes, sir.
115.
Yes, sir.
118.
Present, sir.
134. Maybe he is not present. 134. Are you here? Okay, okay, okay. 138.
Yes, sir.
141. 144.
Present, sir.
145.
Yes, sir.
155. 155. 179.
Yes, sir.
Okay.
Sir, ID 92 এর স্যার 92 না স্যার 93 এর নেট কানেকশন চলে গেছে স্যার স্যার ফোনে ডাটা নেই
আইডি কত?
স্যার 93 আবির
ওকে আমি দিছি হ্যাঁ ওকে let me repeat 16 141 155 and 34 and 149 they will do with other section.
CRK
স্যার আবিদ
ডিসকানেক্টেড হয়ে গেছে
হ্যাঁ ডিসকানেক্টেড হয়ে গেছে
ও না আসছে আবার আচ্ছা আচ্ছা আসছে নেটে প্রবলেম করতেছে
কে CRK
আবিদ
আইডি কত
93 স্যার
আবির ও আচ্ছা আবির 93 আগে না তোমাদের তুর্য ছিল
ইয়েস স্যার তুর্য ছিল স্যার
পরে কি ওকে সবাই মিলে বাদ দিয়ে দিছো নাকি
না স্যার আমি নিজেই সরে গেছি স্যার আমার আব্বু আম্মু অসুস্থ
ও আচ্ছা সরি টু হেড দ্যাট কেমন আছে এখন আঙ্কেল আন্টি
এই তো স্যার আল্লাহ রাখছেন ভালো আব্বু সুস্থ হয়ে যাচ্ছে আম্মু আবার অসুস্থ হচ্ছে
মানে কি করোনা নাকি অন্য কিছু
স্যার করোনা
আবির
ইয়েস স্যার
ক্লাস বোঝা যাচ্ছে নাকি কঠিন মনে হচ্ছে
স্যার আমি লাস্ট 30 মিনিটস ছিলাম না স্যার আমার কারেন্ট চলে গিয়েছিল স্যার এইমাত্র হচ্ছে স্যার
লাস্ট 30 মিনিট ছিল না তাহলে তো তোমার কাছে অনেক ইজি লাগবে ব্যাপারগুলো আর কে আছে
Sir, are you conducting the class from IoT?
For the time being, I am not in IoT. Why?
No, sir, just asking.
No, for the time being, I am not in IoT.
Okay, sir.
অয়ন আছো নাকি 115?
Yes, sir.
কি কঠিন মনে হচ্ছে না সোজা মনে হচ্ছে?
Sir, সহজ।
সহজ?
Sir.
ওকে, আর কে? 13 আইডি 13 আছো নাকি?
Yes, sir.
কিছু বুঝতেছো নাকি কিছুই বুঝতেছো না?
স্যার হালকা সা মোটামুটি স্যার অনেক বেশি একসাথে কন্টেন্ট হয়ে যাচ্ছে স্যার এজন্য
অনেক
বেশি
অনেক বেশি কন্টেন্ট হয়ে যাচ্ছে।
ইয়েস স্যার
আজকে কি কি হলো বলো দেখি এই পর্যন্ত।
না
By
স্যার
the way, we are still in the break, okay? That's why I'm talking in Bengali and something. This is not a part of class.
তোমার স্যার লাস্ট ক্লাসে স্যার অনেক বেশি জিনিস একবারে মানে ক্যাচ করতে পারিনি আসলে ফার্স্টের দিকে ছিলাম পরে গিয়ে আর কনফিউজ হয়ে গেছিলাম পরের পার্টটাতে।
সেটা ঠিক আছে, পরে ক্লাসে পরে একবার নিজে দেখছিলা যে
ইয়েস স্যার ইয়েস
যেগুলি
স্যার
বুঝছো না সেটা
রেকর্ডিং দেখেছিলাম স্যার।
আচ্ছা, আজকের ক্লাসে যতটুকু হয়েছে এটা কি অনেক নাকি? কারণ আজকের ক্লাসের অর্ধেকই তো ছিল আগের ক্লাসের রিভিশন জাস্ট, আর কিছুই না।
ইয়েস স্যার আচ্ছা আজকেরটা স্যার বুঝছি স্যার।
আজকেরটা এই পর্যন্ত বুঝছো?
ইয়েস স্যার।
আর তেমন কিছু নাই শেষের দিকে, এরপরে আর তেমন আহামরি কিছু নাই।
ওকে স্যার।
আর কে 155 রায়হান আছো নাকি? রায়হান আছো?
অ্যাবসেন্ট।
ও রায়হানও অ্যাবসেন্ট, কি আজকে অনেক অ্যাবসেন্ট রে। তৌফিক আছো 145?
Yes, sir.
কি বাসায় না বাজারে?
Sir, বাসায় sir.
বাসায়? কেউ বাজার থেকে ক্লাস করতেছ না তো আবার?
No, sir.
না, এরকম অনেক ঘটনা ঘটে, মানুষ বাজারে, রেস্টুরেন্টে, পার্কে, কত জায়গা থেকে ক্লাস করে।
জি
সবাই
স্যার।
যে অবস্থায় থাকুক শিখতে চায়, এটা খুব ভালো একটা লক্ষণ।
হ্যাঁ তা ঠিক, পজিটিভলি নিলে অবশ্য পজিটিভলি নেওয়া যায়, তাও ঠিক, কিন্তু একসাথে কিভাবে মাল্টিপারপাস জিনিস হ্যান্ডেল করে আমি সেটাও চিন্তা করি।
স্যার ওই ক্লাসে শুধু মানে অ্যাটেন্ড থাকে আর কি, মানে বাজার করতে থাকে মোবাইলে জাস্ট ক্লাসটা অন থাকে আর কি।
মেইনলি অ্যাটেন্ডেন্সের নাম্বারটা না, ফ্রি নাম্বারটা হারাবো কোনো, তাও ঠিক।
জি স্যার।
অ্যাকচুয়ালি লজিক্যাল, স্টিল বেটার। ফ্রি
আর
নাম্বার
রেকর্ডেরটা দেখে নেবে আর কি।
হ্যাঁ, না আইডিয়া খারাপ না, অন্তত ক্লাসে মানুষ থাকলো। মাঝে মাঝে আবার অনেকের মাইক্রোফোন হুটহাট আনমিউট হয়ে যায়, তাহলে বাজার টাজারে থাকলে এটা খেয়াল রাখো, মাইক্রোফোন যাতে হুটহাট আনমিউট না হয়। আচ্ছা, অনেক ব্রেক হইছে, সো লেটস স্টার্ট। Okay, so let's start. So unsigned and signed interpretation. So as I said, we will be discussing why it is said as unsigned and signed interpretation. So for the timing, we know that if our MSB is 1, the number is negative, as you can see over here. Whenever the MSB is 1, the number becomes negative, and otherwise the number is positive. All right, let's move on.
How is 101 in unsigned equal to -3? Because if we consider the MSB,
you will get that. We will get to that portion. Yeah, I mean, don't assume that this 1 is for minus and then 01 is for 3. Nothing. It is not like that. You will get to know. Okay.
Okay.
How it is becoming what. Okay, let's move on. So first of all, you need to know how to find 1's complement. So this is what we just discussed. MSB 0 is positive, MSB 1 is negative. So now it will answer your question. 101 is equal to minus n, right? 101 is -3. So how do you know which one is 3? So the first thing you need to do is you need to find the 1's complement. So 1's complement is whatever bits you have, you simply alter or reverse those bits. So you have 101. So the reverse of 1 is 0, 0 is 1, 1 is 0. Very simple. Clear? 1's complement?
Yes, sir.
Very simple.
Yes, sir.
With 1's complement, you add another 1. Simple binary addition. Okay, remember this is your binary addition. You add another 1 and you end up getting 3. So minus n is actually n. So very simple. For any number, if you want its minus, you find the 2's complement. This one is known as 2's complement. First of all, you find 1's complement. With the 1's complement, you add another 1 in binary. The result that you get is the 2's complement of this number. So the 2's complement of, okay, let me write over here.
Sir, n টা কি randomly assign করছে?
Exactly, any number. So your 2's complement of x is minus x, whatever is your x.
Yes, sir.
2's complement of minus x is what?
X.
X. Very simple. So whichever number you have, if you simply find the 2's complement, you will find the negative of that number. So whichever number you have, if you find the 2's complement of that number, you will have the negative of that number. So negative of minus x is x. Negative of x is minus x. Did you get the answer to your question that you asked in the previous slide?
Yes, sir.
Clear up to this?
Yes, sir.
Okay. It will be much more clearer. Don't worry. There is another way to find the corresponding number, and that is subtracting the highest. Like we know that our address, sorry. Okay. We know that we have got a 20-bit address bus, right?
Yes, sir.
For simplicity, we are assuming 3-bit. The same thing, if you understand for 3-bit, you can apply for 20 bits as well. So for 3-bit, your signed decimal is equal to your unsigned decimal. I mean, this is very simple if the MSB is 0. There is no problem with when the MSB is 0. The problem occurs when your MSB becomes 1. So when MSB becomes 1, if you want to find the original number, you can follow the 2's complement method. Another method is this one. Your signed decimal will be equal to the unsigned decimal minus 2 to the power 3 for 3-bit. Is it clear?
Yes, sir.
Try to understand. Your 111. What is your 111? Your 111 unsigned decimal is 7, isn't it?
Yes, sir.
Sir.
Minus 2 to the power 3, which is 8, because this is for 3-bit. If you want to go for 20-bit, you have to subtract it from 2 to the power 20. Very simple. If you want to go for 16-bit, you have to subtract minus 2 to the power 16. Right? So this is another method by which you can get your corresponding signed decimal value.
Yes, sir.
Any question up to this?
No, sir.
No, sir.
Easy, simple?
Yes, sir.
Okay, let's move on. So I wanted to add this portion, how to easily convert between hex to binary and vice versa. Are you guys familiar with, okay, yeah. Are you guys familiar with 8421 rule?
Yes, sir.
Are you familiar?
Yes, sir.
Yes, sir.
Everyone, are you familiar? Is there anyone who does not know this thing? Anyone?
So these are the weights of binary numbers.
Yeah, I'm asking, is there anyone who does not know this rule? Then I will not discuss it actually. Anyone? So I believe everyone knows. See, if there is anyone, you need to respond. That, sir, I don't know. Please explain. So I will explain. Otherwise, I'll not explain. All right. So let's assume that since none of you are saying anything, so I'll assume that all of you knows this, right?
Yes, sir.
Still, let's take a few example. If I write 55H, what is the corresponding binary?
Sir, 01010101.
0101
0101.
0101. If I write 62H, what is the binary?
01100010.
Yes, sir.
01100010. Yeah, simply. So we placed 1 on these values. So 1 in these 2 bits. So 4 plus 2 is 6. That is for 6. For 2, I need only 1 in this portion. So all of them are 0 and this is only 1, right? You already know this thing.
Yes, sir.
So conversion between hex to binary and binary to hex is very simple.
Yes,
now,
sir.
There was another thing I want to ask. Why do we use hex? I mean,
Sir,
we are already familiar with decimal operations and everything, right? So instead of hex, we could have simply gone for decimal. But why are we using hex?
Sir, compact calculation.
Okay, anyone else?
Sir, I have another reason that hex it takes less bit, less number to say present a long number in hex, but in cases of decimal, we're gonna need more numbers or bits.
Okay, all right. Anything else? Okay, anything else?
Sir,
All these are
this
true.
is a 16-bit processor and hex is also on 16 base.
So that means if we ever use 32-bit processor, we cannot use hex, right?
I don't know, sir, maybe.
All right, all these answers are right except the last one. Okay, this is not for the based on the processor. The reason is for decimal, what we have 0 to 9. What
Yes,
is
sir.
the binary of 9? Tell me, what is the binary of 9?
1001.
You are applying the 8421 rule. Can we represent 9 in 3-bit?
No, sir.
No, sir.
What is the highest number that you can represent in 3-bit?
7.
7, sir.
Okay, for 7, what is the binary?
111.
Okay, 111. So for 8, what is the binary?
1000.
1000.
1000. For 9,
Sir, 10001.
Okay, now see, if we had gone for decimal interpretation, for up to 7, our 3-bit was sufficient. But for these two representation, we need 4-bit. But then again, in 4-bit, we can have 16 combinations, right?
Yes, sir.
So rest of the combinations, I mean, after these two, the rest of the combination becomes or are unused in decimal if we had gone for decimal. So what to do with those combinations? You cannot just simply leave them blank. To solve this problem, your hex came into place. Because in hex, we have got a total of 16 combinations. And that's why using entire 4-bit, we can represent all the numbers of hex. Is it clear?
Yes, sir.
In decimal, if we had only 7 combinations, we could have used 3-bit that could have solved all our problems. But unfortunately, that is not true. Because we have 8 and 9 as well. Is it okay? Why we move to hex? To make a complete utilization of 4-bit or any combination of bit, 2, 3, or 4-bit, anything, it has to be something similar. So in order to make complete utilization of 4-bit, we move to hex. Clear, everyone?
Yes, sir.
This was the primary all those advantages are actually derived from this concept.
Sir, can you repeat, sir? What was the primary? Your internet was interrupted.
Yeah, I think I'm having some internet issues. All right. So this was the primary reason, that is to make a complete utilization of all the 4-bit combination. All right. Whatever advantages all of you said are actually derived from this advantage or this primary reason. Clear, everyone?
Yes, sir.
Yes, sir.
Okay, let's move on. So now we have got a math. Find the 2's complement of 5 and then add the answer to 5. And we need to do the operation in 16-bit. All right, so let's do it together, okay? So if we write 5 in decimal, what is the binary representation in 16-bit?
So 101.
Tell me. 16-bit. 0 অনেকগুলো কতগুলো রে ভাই?
12টা 0 তারপর 101.
Okay, so 0
0 0 0
then again 0 then
0 0 1 0 1.
All right, so this is what binary, I mean what 5 looks like in binary.
Yes,
so in order to find 2's complement, what is the first thing that we need to do? We need to find 1's complement, isn't it?
Yes, sir.
Exactly, 1's complement. So let's write 1's complement. So what will be the 1's complement? 1 1 1 1 1 1 1 1 1 1 1 1 0 1 0. Okay, clear up to this?
Yes, sir.
Sir.
Up to 1's complement, is it clear?
Yes, sir.
Yeah, any question, please ask. কোনো question?
No, sir.
Okay. After finding 1's complement, in order to find 2's complement, what do? We add, isn't it?
Yes.
Okay, so 1 plus 0 is how much? 1. Again this one.
1.
1. This one.
0.
So rest of the things will be same. So this is my 2's complement of 5. Is it clear up to this?
Yes, sir.
Yes, sir.
So in decimal, what is it supposed to represent?
-5.
It is supposed to represent -5.
Yes.
Now this part is complete. We found the 2's complement of 5. What is the next thing? Then add the answer to 5. So we need to add 5, isn't it?
Yes, sir.
And we already know this is the binary representation of 5. So let's just write 1 0 1 0, and all these are zeros. Okay. Okay. We need to add this, and over here we have got the decimal addition. So in decimal, what is our answer?
0.
0, sir.
Okay, so let's see what we get in binary. 1 plus 1 is how much?
0.
0.
Carry 1.
1 carry, then
0. Carry 1.
then
0.
All 0, there will be 1 overflow.
exactly. So all will be 0. You get the point, right? Everyone,
Yes,
is it
sir.
clear?
Yes, sir.
Yes, sir.
Finally 1. So this is your answer, isn't it?
Yes, sir.
But
Yes, sir.
what is the
One
address? I
should
mean,
be
what is it? It
discarded.
is 16-bit, right?
Yes, sir.
So only this 16-bit will be accountable for your answer. So what does this 16-bit represent?
0.
0.
0 in binary. That is exactly what you got in decimal. Is it clear now?
Yes, sir.
Yes, sir.
Everyone, is it clear?
Yes, sir.
If you are ever given to find a 2's complement of any number, can you do it?
Yes, sir.
Yes,
And
sir.
can you verify whether the answer is right or wrong?
Yes, sir.
Yes, sir.
Any question over here, please ask.
No, sir.
No question?
No, sir.
All right, let's move on. Okay, so there was a thing I said you that I'll explain what is the meaning of interpretation. So here is a question. Add FAH with 01H and interpret the result. Now I have already done a few things for you. Your FAH, yeah, say. I don't know. Robil gonna prove us, re?
Actually, what does it mean by proof? Like,
Actually, yeah.
Basically, say for 101, for 3, okay, for 101, what we have got? The 2's complement. 0 1 0, then adding 1, that means 0. Okay, for this one, 101, for 101 you are getting 0 1 1, isn't it? So basically, what I understand, that this is just a relation, relation. That means the highest number, okay, 111, that will be -1, and like that. So actually, I should say there is a rule, or there is a system that we can convert. Let's see.
Anyway, we should not say that. Wait. We should not say that your question is not valid. But actually, we have never faced this type of question in our entire, what I can say, lifetime. We have never
As
even
far as I know, it's not just altering the digits. It's like it is a 3-bit number, so the 3-bit highest number is 111. We are we are taking the difference from 111 to 010 or 101, and after that we are adding 1. This system works in other digit system like decimal and others.
Yes, sir. We can also apply
I think we can find some explanation from there.
Yes, say again. Let me try to understand what you are saying. Okay, explain again.
লাইক স্যার এখানে হচ্ছে আমাদের 3টা ডিজিট, সো আমাদের বাইনারিতে 3টা ডিজিটের হাইয়েস্ট হচ্ছে 111. সো আমরা এখানে জাস্ট অল্টার না করে 111 থেকে এই নাম্বারটা হচ্ছে বিয়োগ করতেছি.
So that is what you are saying about this one, right? This is what we just, this explanation you are saying.
জি স্যার, এটা হচ্ছে মানে জাস্ট বাইনারিতে না, অন্যান্য ডিজিট সিস্টেমেও কাজ করে. সো আই থিংক এখান থেকে কোনো একটা এক্সপ্লেনেশন পাওয়া যেতে পারে.
আচ্ছা, so মানে you are saying that এইখান থেকে this can be derived?
Yes, sir.
Maybe, I don't know, might be. বলো। হুম হুম like I said, I really don't know the clear cut answer, but this may be. But at least this is good that sometimes we fail to make understand the two's complement, and now you're asking questions why we are going for two's complement, why is the method like this. So this is a good thing. So that does mean that at least you understood two's complement, which is my primary goal. Is it okay?
Yes.
The rest of the things, definitely you can Google it if you want. In the next class we can discuss, so I can also learn, or we can also learn from you guys. Okay.
Yes, sir.
Okay, so I think in this slide. All right. So now, as I said, we need to explain why we said interpretation. So the question is, add FA in hex with 01 hex and interpret the result. So this is the question, and I have done a few helping for you. Like in FAH is -6 in signed interpretation and 250 in unsigned interpretation. This is the decimal representation. If you want, you can check that also. That is totally up to you. And this is the binary representation. And 01 hex is 1. Very simple. There is no signed and unsigned because the MSB is 0. So it will be the same thing in decimal, unsigned and signed representation. And this is the binary representation. So if I now add these two, what will be my answer? Did you get the problem actually?
-5.
See, so if you say -5, exactly, that's what I'm trying to explain over here. So first of all, tell me the answer in binary. That is the first thing I need. Tell me the answer in binary. What will be the answer?
Sir, 1 1 1.
Aste. You are going from right to left or left to right?
Left to right.
Left to right. Okay, tell me. Let me write over here your answer. Tell me. 1 1 1. First of all, 3 1.
Pasta 1 sir, তারপরে 0 1 1.
আচ্ছা আচ্ছা পাঁচটা 1. আচ্ছা চারটা 1. Okay, 1 0 1 1. Acha, this is the answer.
Yes, sir.
All right. Now, what is the decimal form of this?
251.
251. That is if you consider unsigned, right?
Yes, sir.
Yes, sir.
If you consider signed, what will be the what is the signed representation of this one? -5 to -6 or 1 kore easily bolla -5, but actually what should you do? You should find the 1's complement first, then find the 2's complement, isn't it? So this will be -5. This is your signed interpretation. What is the answer in hex? I mean, if I convert this number to hex, what should I get? F
B FB
FBH in hex, right?
Yes, sir.
So you see, you got all these things. So now I said interpretation, try to understand this portion. So when you command the microprocessor to add these two portion, okay, when you command the microprocessor to add these two portion, your microprocessor will end up getting this answer, right? This is what your microprocessor will do, because your microprocessor does not know what is signed, what is unsigned, what is this, what is that. He doesn't know. I mean, it doesn't know that. So this is what you will get. So now it is up to the programmer to decide what he means. If initially he intended for signed operation, then he will say the answer is -5. If initially he intended for unsigned operation, he will say the answer is 251. But in hex, his answer will be FBH. Is it clear why I said interpretation?
Sir.
The answer that will be stored in microprocessor is this one. because your microprocessor knows nothing but zeros and one. That is the binary language. So your microprocessor will store this answer. What you understand by this answer is totally up to you. That's why it says interpretation, because the programmer needs to decide what he means by this particular number, because it means all these things. So what he means is up to him. Clear, everyone?
Yes, sir.
Yes, sir.
Any question you can ask.
So, sir, if since there is a liberty to decide between signed and unsigned,
Of course,
so,
there is a liberty.
So, won't the programmers all over the world get confused with each other?
Why will they get confused? Each particular program has a specific target or a specific aspects. That is how the program is built. So if the programmer initially initiated or designed a program which will consider only signed, then definitely he will have this instruction somewhere that consider everything in as signed interpretation, consider everything as unsigned interpretation, isn't it? He will have those things.
Yes, sir.
So of course, because you need some way to represent the minus numbers. So how will you do that? You can't generate a whole new system.
Yes,
because
sir.
you have only zeros and ones. With zeros and ones, you need to represent each and everything of this world. So there has to be some way, and this is the way. Any
Yes,
other question?
sir. No, sir.
Anything else?
No, sir.
Okay, so let's move on. Okay, so from this point onwards, I think Robil will take the following question. Robil.
Okay, you can stop sharing so that I can share. Okay, just maybe 3-4 slides left, and just last day maybe someone has asked that about the memory mapping. Just an idea. At the middle of the class, Arif have already told you that these are not that much simple that we are talking. Obviously, we have more to learn, and I do not know whether it is possible to cover in lab, because we have to learn assembly language and all this thing, and in a single lab it is not possible to learn everything about a single microprocessor and how it works and all those things. But even after that, we try to incorporate few things. So if I say the whole map, about the whole mapping, I have you know that it is 1 megabyte. So this is the breakdown. Okay, by 1 megabyte, actually we are saying that to the power 20. That means this number of addresses can be accessed. But the circuit diagram, or if we say the circuitry of ROM and RAM are different. Okay, I'll ask 88. Can you please respond?
Yes, sir.
Okay. So what I'm saying, have you understood that part?
Yes, sir. Total 2 to the
That
power
RAM
20.
and ROM are different thing.
Yes,
But
sir.
we can address RAM and ROM using those address buses. But the circuitry of RAM and ROM are different. So what I'm saying, that we can address to the power 20 addresses. That is the thing. We can address RAM or ROM, but their physical condition can be different. Okay. Now here is the just breakdown. In RAM we have total 356, out of which we have a BIOS. Okay, just it is basic input output system. I'll come to that point later. So BIOS is basically stored in ROM. That means which will not be erased even if you switch off the power. So and there is video display, and that is the part of ROM. That means whenever you have something to give output, there are a few data that needs to be stored. So from your book, you can okay. By this time, just I'm trying to add here that I will request you to go through. We have covered chapter 1, and we have included more things in chapter 1 from Marut's book. So you can just go through the book, and obviously we're preparing these slides to make the things easier to represent to you. but you should go through the book. That is my suggestion. You should go through and the book is written in very simple language, so you will understand that part. So
Yes,
here,
sir.
yes.
Yes, sir.
Yeah. Okay. So here is basically the breakdown. You can say this part is basically your RAM. Okay, let me go to. So this portion is important. When you power up, how an startup operation works. How an startup operation works. So basically, before that, here two things I need to discuss: the BIOS and DOS. So DOS is basically for 8086 is called disk operating system. So in our processor we have also operating system. Someone is using Windows or some other things. So basically DOS or any operating systems, and whatever we are calling, this is either ROM or RAM. This is not your hard disk. Your hard disk is basically a input output device. That is not our memory.
Yes, sir.
What we are discussing. Is it clear? So
Yes, sir.
basically the program, or the, what should I say, in hard disk you can save the operating system, and whenever you switch on or power on the PC, so then from the ROM it gets the program which actually load that operating system to the RAM, not fully, the portion that is needed to be loaded. So when powered up, RAM is basically empty. You do not have anything in the RAM portion. So how the operating system loaded? That is the thing we are trying to explain here. So in the book, you can also get this in chapter 3 and 3.3.4. So far I can remember. So you can go through that part. So whenever you power up, RAM is in. But in this case, the CS and IP, there it has FFFF and 000. These two will be saved initially. When you powered on, CS and IP will have this value. All the 16 bit is 1 for this, and all the 16 bit of IP is 0. So if we have segment and offset address, then we can get the physical address. So this physical address is basically a physical address of BIOS portion, basic input output portion. That is which of this one is a ROM inside the ROM. So that will not be erased. So this memory location in the ROM basically contains an instruction that transfers the control to the starting point of BIOS routine. So here you can get confused with routine. Routine means you can say a set of programs, or a set of program with different objective, you can say. So that basic input output device has different routines. One of them is at the beginning. So what happens if I go from the beginning? First, when you power up, the RAM is empty, but ROM has the previous things, because that will not be deleted. Second, what happens? Basically, your CS and IP will have these values, and these values will get the physical address. So third, this physical address is basically having an instruction that transfers the control to the starting point of the BIOS. So BIOS basically, it is fixed that in the ROM, the BIOS starts from this F0000 and it's end at FFFFF, the physical address. Is it clear?
Yes, sir.
So then whenever this particular, so FFFF0, this has a particular instruction that takes that instruction, transfer the control to the starting of the BIOS. So basically this is something in the middle, but it is easier to set CS and IP to 00 and 11 at the beginning. Okay, whatever. So then the BIOS routine starts executing. So if I go to the next slide, then what does the BIOS routine does? So it actually checks the system and memory errors first, then initialize the interrupt vectors of BIOS and data area. So the interrupt vectors, you have seen, you can see here, this is the interrupt vectors. Okay, interrupt vectors is maybe we'll discuss in the next lab, hopefully, but for the time being, if you want to take any input from the keyboard, or if you want to show something to the monitor, you need those interrupts. Like you want to you need to wait for something. So the input output devices basically contact with the microprocessor using the BIOS interrupts. So we'll discuss about those interrupts, inshallah. And then after that, it loads the operating system. This operating system basically loads in two what should I say, by two operations. So BIOS loads a small program called boot program. First of all, from BIOS, a boot program is installed, is executed, and after execution of the boot program, this boot program basically loads the operating system from your, maybe that will be your hard disk to the RAM. The operating system will be loaded, and after that, the BIOS or boot program will give the control to this particular operating system that will be running. So is it clear, the total procedure of starting up of the operation of any microprocessor? Any confusion up to this? Anyone?
Yes, sir.
Okay.
No,
So I
sir.
hope that okay. I hope that you have understood. So now we'll show a code in emulator just to give you an idea. Okay. Before that, these are the home tasks, and basically this home task the same thing like the previous one, and maybe you have already turned in a few of the assignment, and I'll create the next assignment inshallah next day. So just same thing, you write down those things and make the PDF and upload that in Google Classroom. Okay, now let me share the whole screen so that I hope that all of you have installed the emulator.
Yes, sir.
8086. Yes.
Yes, sir.
Okay, this is your emulator. Let me take this one. So the initial interface. So I have some written program. So just let me open that one from there. So the first program can be the hello world. So if you want to just print hello world uh, in assembly language in emulator. So basically what emulator does, you can write, this is just a text editor. Okay, first of all, you write the code, then when you press this emulate, it will make the program executable. It will make the program executable, and then from here you can run, and or you can go single step, and you can go different way. Just okay, before going to there, so in the next class basically we'll discuss what does this dot model small means, what does the stack means, what does dot data constraint, what are the things that dot code actually. So that is the main the dot code has the coding part, and dot data, dot stack, these are the things that we'll be learning in the next class. So the string that you want to that we want to show in the in the output. So let me run this one. Okay, that is your that is basically your output. So you can if I say these are the different parts of the code, then obviously we'll learn this particular code in the next class, and we'll learn how this thing works and how it ends and how it all the things works. So, and another thing is that here is the interface of your, whenever you make it executable, here you can find different registers here, AX, BX, CX. So whenever you run a code, then okay, you need to terminate. Yes, I have and reload it. So whenever you go single step, then you can see move AX. Okay, if I go back, there's the first code is move AX comma something, the address of something. So it has I have beforehand, you know that this is a 3 bytes operation, AX, and maybe one operation has been shown in the last class, that which instruction is how many bytes. So these are the machine code, you can say B820. Can you see my mouse cursor? Okay, these are the representation in decimal, that binary hexadecimal and decimal. Then there is the ASCII code. Have you heard the term ASCII? ASCII.
Yes, sir.
ASCII value. Yes, yes. So if you want to print something, we need to know the ASCII value of that particular character. Is it okay? Another thing is that these are the register. You can see BX, CX, and we can debug. We can see how the things are changing. So initially this AX is 0, and if I just go for a single step, then you can see AX values has been changed, and it is going to the next line, and the corresponding machine code is here. And in the left, you can see these are the address. So here the segment address and offset address. So the segment address is 0721, and that is the offset address, and these are the physical addresses. 07210, the first address, then the second, third. These are the physical addresses. So if I say what is the value of what is the value of CS, what will be the answer? 21, not 0, because 0 is the physical address. If you have 5 bits, that is the physical address. So CS will have only 0721. And also you can see here CS. You can find CS here 0721. CS is having what?
0721.
Yes. And also another thing is that an IP will be pointing to the next. So our first instruction has been executed, and we have not executed the second one yet. So we have executed the IP address of 0, 1, and 2. So the IP is instructing to the next one, 003. These are the thing we have already learned, isn't it?
Yes, sir.
Yes. So and SS, ES, DS, these are what? These are the what should I say? The segment addresses. So from here you can have those things. And also today you have heard about the stack. You can obviously just click. Okay, it is coming to my next window. So you can also find how the stack is looks like. So I don't know how to take this to. Okay. What is that? Oh, nope is a okay. That is a what should I say? Nope is an instruction, obviously. Nope means no operation. You'll learn that in the next class. So basically, our code ends here, and after that, that is the part of the emulator to go on basically. So if you see the code, on last line was interrupt 21H. So we'll discuss what does this means and all those things. So but no is basically, if you say what does that mean, that is called no operation. There will be no operation, but the cycle will be going. So if you want to give a pause after running something, so you can run that in a loop. So for 1 second, if you can want to give a delay of 1 second, then you can use that no. Or there are many other things. So you can debug like this. Okay, you can see the flags. Okay, already maybe in some window is still flags. Don't know where it is. So even you can see the flags, how the flags will be changing with your okay, it is in the other window. So the flags that you can see here, so that will be changed in after every operation. You can, maybe we'll see that those things in the next classes. This zero flag is 0, that means the number after the execution is positive, and the sign flag is 0, that means there is the MSB is 0. So all these things you learn those things inshallah in the
Yes, sir.
next class. Have you got my point? So
Yes,
just
sir.
I want to give an idea how the things work. So here we'll write the code, and also before coming to the next lab, I'll suggest all of you to install this one and to make it working, so that we learn. And there are so many rules you'll be learning, because in MATLAB also you have some rules, and as it is a lower level language, it has more rules. If we just want to write you want to, what should I say? Let us say you have a 16-bit number. You want to move it to AH. That will be error because it cannot take more than 8-bit. These are there are some rules obviously, and these are not written anonymously. Obviously, there are some rules. So in the next lab, we'll learn maybe few other things, and you can see here one program that we'll see that from lowercase to higher case. Okay, if we run this program, then you can see enter the letter in lowercase. So if you enter G, that will be in uppercase, it is G. So you need to, your program is almost 37 lines to do only this code. So just you print something, scan and print, that will be in C programming. But here you need to do all these things manually.
Yes,
So
sir.
these are the things, inshallah, you will learn in the next class. Arif,
Yes,
should
sir.
I discuss anything more? Arif?
I think that is all. When you come in the next class, like today, for the first 10 to 15 minutes, again, you will be asked some questions randomly. And it will be based on first 2 labs, because today in the first around 15 or 30 minutes or 20 minutes, we discussed whatever we had covered in the first lab. So in the next lab, you will be asked questions based on the first 2 labs that we had. Is it clear?
Yes, sir.
So please make sure you have a fair, what I say, a fair preparation, because if you don't have sufficient amount of preparation of understanding all these things, you will not understand anything in the next lab, because we are entering the code portion. So you really need to understand the first 2 labs very carefully. So please go through the first 2 labs before you come to the next lab. Okay.
Okay, sir.
Yes, sir.
Just one more thing, you can find ASCII codes here. If you just click there, this ASCII code will be here. These are in decimal and hex representation, all these things. This is, I should say, okay, why we are using emulator, maybe we could have used our MASM. That is okay, I will discuss that inshallah in the next class, not today because it is already 12:50. That's it.
Okay, sir. Assalamu alaikum.
Okay, if you do not have any question, I think you can leave. And if someone has any question, then maybe we can wait for 1 or 2 minutes.
ID 93 sir, attendance dite parini sir.
Yes, I have given, I have taken that as a note.
Sir, ID 155, sir, attendance missing maybe.
Yes, but we have called you several times. Maybe Arif was searching 155. Arif.
আমি আর কি randomly maybe I was searching for asking questions.